Welcome back. In this video, we are going to solve problem 6-25 that is taken from chapter number 6, Bending, and book name is Mechanics of Material by R.C. Hibbeler. So statement is draw the shear and moment diagram for the beam and determine the shear and moment in the beam as a function of x, where x is greater than 4 feet and less than 10 feet. So you can see this is the beam, clear, where the loading is shown. There is a counterclockwise movement of 200 pound into feet at this point, and at this end we have also 200 pounds into feet, that is clockwise, clear. And from A to B there is a uniformly distributed load of 150 pounds per feet. There is a roller support at A, and at B we have a pin support. So you have to find the shear force and moment diagram, and then shear and moment as a function of x for the region x is greater than 4 feet and less than 10 feet. So let's start with the solution. So first step is that if you remove this roller support at point A, so you will be having a reaction force which is Ra, and if you remove this pin support at point B, so you will be having a reaction force which is Rb. We will find this Ra and Rb by using equation of equilibrium. So first equation of equilibrium is that sum of all moments about point A is equal to 0, and taking the counterclockwise moment as positive. So first moment is this 200 which is counterclockwise, so I will write 200. The second moment will be due to this uniformly distributed load, and when this is converted into a point load, so it will be equal to 150 over the length over which it acts, and that is 6 feet. So it will give you 900 pounds, clear. And that will act at a distance of 6 by 2, means half of this length. So this will be 3 feet from this side, and from the remaining this will be also 3 feet. So second moment will be due to this load which is 900, and perpendicular distance is 3, and this is clockwise, so it will be negative. So I will write minus 900 into 3. The fourth movement, the third movement that is produced due to this RB into perpendicular distance is 6, and this is producing counterclockwise, so it will be positive. So I will write plus RB into 6. And the last movement that is produced due to this 200 pound into feet, that is clockwise, so it will be negative. And the sum of all these movements about point A must be equal to 0. So this will cancel with this, so we will left with 6RB is equal to 2700. So when you divide 6 on both sides, so you will get RB will be equal to 450 pounds. Okay, so now we'll find this Ra by using another equation of equilibrium, that sum of all forces along y direction must be equal to 0, and upward forces taken as positive. So you can see one force which is Ra, that is upward, minus this 900 pound force plus this 450 which is RB is equal to 0. So from here you will get Ra will be also equal to 450 pounds. Okay, so now we will move toward our second part, that is to determine the shear and moment as a function of x, where x is greater than 4 feet and less than 10 feet. So what we will do is that you have to cut the beam it in this region, and this will be the x, and you have to draw the free body diagram for this portion. Here, so let me draw it for region for x is greater than 4 feet and less than 10 feet. When you cut the beam, it will be like this. There is a moment at this point which is 200 pounds into feet. This is let point A, where you have 450 pounds load is applied. This is point A, and when you cut it, you will be having a shear force which is this, and you will be having a moment M as well. So from this point A, we have a uniformly distributed load till the end, and this uniformly distributed load is 150 pounds into feet. The total length is from this till this distance is x. So this remaining distance, you can see this will be, this distance is 4 feet. So this distance remaining will be 4x minus 4 feet. Okay. Now what we will do is that we will find this v and m by using equation of equilibrium. So first equation of equilibrium is that sum of all forces along y direction must be equal to 0 and upward force is taken as positive. So you can see one force which is 400 pound, that is acting upward, so it will be positive, minus this v is acting downward. You can also take downward because you have to take it downward because you can see this is upward, and in this remaining portion all the forces are downward, so shear force will be also downward. So minus v, and when you convert this uniformly distributed load into point load, so it will be equal to 150 into length over which act, which is x minus 4, and that will act at a distance of, this distance will be equal to x by 4 divided by 2. Okay, so the load is 150 minus 150 into x minus 4 is equal to 0. So when you solve this, you will get 450 minus 150x minus plus, so 150 is 600. Clear? And that will give you 1050 minus 150x. This is the equation of shear force for the region x is greater than 4 feet and less than 10 feet. Now we'll apply another equation, that is sum of all moments about this, let this is 1.1 is equal to 0 and taking the counterclockwise moment as positive. So about 0.1, one moment will be this one, this is 200 and counterclockwise, so it will be taken as minus 200, so minus 200 is this counterclockwise. The second moment about this point 1 will be 450 into perpendicular distance is x minus 4, and this is producing clockwise, so it will be negative. So I will write minus 450 into x minus 4. The third moment will be 150 into x minus 4, and perpendicular distance is x minus 4 divided by 2, and this is producing counterclockwise movement, so it will be positive, and sum of all moment about 0.1 must be equal to 0, and this moment is positive because this is counterclockwise. Okay, also you can see there is a external movement, so I will add this m as well. Now we will simplify it, so m plus 200 minus 450 into x minus 18 minus minus plus, so 1800 plus 150 divided by 2, and this will be x minus 4 whole square, which is equal to x square plus 16 minus 8x is equal to 0. So m will be equal to m plus 200 minus 450x plus 1800, 150 divided by 2 will be 75, so 75x square plus 75 into 16 will be equal to 1200 minus 75 into 8 will be 600. 600x will be equal to 0. So m will be m plus 200 plus 800, 1200, and 2000, and 1200 is 3200. So m plus 3200 plus this 75x square, clear, and this will be minus 450 plus minus 450 and minus 1600, it will be minus 1050x will be equal to 0. So from here m will be equal to minus 75x square plus 1050x minus 3200, and this is the equation of movement for the region x is greater than 4 feet and less than 10 feet. Now we will draw the shear force and bending moment diagram. So for that I will take vertical lines from the end of this beam. Clear? Let me take it, and we will draw a horizontal line in order to show the shear force. X will be in feet. Here y-axis we will take shear force, that will be in pounds. Now you can see at this point there is no shear force. Clear? So from this point till A, the shear force, it will be the same. It will be 0 till this point. This is your point A. Now at A we can see we have RA, which is equal to 450. So let one division is 150, 250, and this is 450. So shear force will change from this till this point. Okay. Again, you can see that you have this equation of shear force for the region x is greater than 4 and less than 10 feet. So this is 4 and this length is 10 feet. So you can just put it, for example, if you put x is equal to 10. Clear? So 150 multiplied by 10 is 1500. So plus 1050 minus 1500 will be equal to minus 450. So at this point we will have minus 450. So minus 450 is this one. Clear? This is the point minus 450. This is plus 450. And you can see that shear force is a horizontal line and downward. So bending moment will be 1 degree higher and it will be a straight line and slope will be decreasing. So you can join these 2 points using a straight line. You can also put the value of x at any x, so you will get these points. Clear? When you put x is equal to half of this will be 3 plus 4 is 7. So when you put 7, v will be equal to 0 over here. This is 7 feet. Okay. Now from at this point we have RB, which is equal to plus 450. So shear force minus 450 and plus 450 will bring it to 0. Clear? From this point. And you can see there is no other shear force, it will be remain horizontal. So this is your shear force diagram. Clear? Now we will move toward drawing bending moment diagram. So for bending moment diagram, I will take a horizontal line. X will be in feet and we have moment that will be pounds into feet. Clear? Let one division is equal to 200, so it will be 200 plus 400 plus 600. Similarly, minus 200 minus 400. Now at this point you can see you have counterclockwise movement of 200 pounds into feet. So while drawing the bending moment bending moment diagram, it will cause the movement toward negative side downward, because this is given and this is convention mentioned in the book. So your first point will be this one. Clear? Now from this point till point A, there is no other movement, so it will remain horizontal up till this point. So this will be remain like this. Okay. At this will be minus 200. Now you can see that you have this is the equation of movement. Clear? So at x is equal to 7, because here shear force is 0, so bending moment will be maximum. So this is x. So put x is equal to 7 in this equation, so you will get moment will be equal to 475. So you will plot this 475 5. So 400 is this one. This portion is 475 will be somewhere here. 475. Okay. Now you can see that this shear force is 1 degree line and slope is decreasing. So bending moment will be second degree curve and it will be like this, and it will be in clockwise direction. So I will draw it like this. Here. Okay. Now for x is equal to 10 feet at this point. Clear? So when you put x is equal to 10 in this equation, so you will get moment will be equal to minus 200, which will be this point. At this length, this will be like, it will be like minus 200. And you can see that this shear force is again a straight line with slope and decreasing. So bending moment will be second degree curve and it will be in clockwise direction. So we will join the same thing like this. It will be like this in curve form. Okay. Now there is no movement from point B till end. So it will be straight line. Clear? And at the end you can see you have a clockwise movement, which when drawing on a bending moment diagram, it will cause it to move upward. So minus 200 plus 200 will bring it to 0 at this point. I will join this, and this will be your BMD, bending moment diagram. And that was all about this problem 6-25. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching and supporting me. Welcome back. Problem 6-36. This problem is taken from chapter number 6, that is bending, and book name is Mechanics of Material by R.C. Hibbeler. Statement is the shaft is supported by smooth thrust bearing at A and smooth journal bearing at B. Clear? Draw the shear and moment diagram for the shaft. So you can see this is the shaft where there is a smooth thrust bearing at A and smooth journal bearing at B. And at this point we have a load of 900 Newton, and at this point we have a moment of 600 Newton meter in that is clockwise. So you have to draw the shear and moment diagram for the shaft. So let's start with the solution. So first step is that you can see there is 900 Newton load that is acting downward. So if you remove this smooth journal bearing at point B, so you will be having reaction force that will be upward, and let this is RB, and if you remove this thrust bearing, so this force will be downward, which is equal to RA. So you can find RA and REB by using equation of equilibrium. So first equation of equilibrium is that sum of all moment about point A is equal to 0, and taking the counterclockwise moment as positive. So about point A, the first movement will be due to this force, which is RB, and perpendicular distance is 1.6 meter, and this is producing counterclockwise, so it will be positive. So I will write RB into 1.6. The second movement will be due to this 900 Newton load, and perpendicular distance is this 2.4, and this is clockwise, so it will be negative. So I will write minus 900 into 2.4, and third movement is this 600 Newton into meter, that is clockwise, so that is minus 600, and their sum must be equal to 0. So when you solve this, you will get RB will be equal to 1725 Newton. Now we will find this RA by using this equation of equilibrium, that sum of all forces along y direction must be equal to 0, and upward force is taken as positive. So RA, which is acting downward, so minus RA plus RB, which is 1725 minus 900 is equal to 0. So from here you will get Ra is equal to 825 Newton. Now you have Ra and Rb, so we'll move toward drawing shear force and bending moment diagrams. For that, I will draw a vertical line from the end of this shaft or beam, which act as a beam here, and you have to first draw the shear force diagram. So again, I am going to draw it over here. So this is the length x in meter. Here we will draw the shear force and the unit will be in Newton. Let one division is equal to 200. So 200 plus 400. Okay, we are going to convert it into 300 due to limitation of space. So 300, 600, and this will be 900. You can select it as per your own scale. So minus 300, minus 600, and so on. Now you can see at point A we have RA which is acting downward, and RA is 825. So our first point will be 825. So this is 600. So this is minus 900. So 825 will be somewhere here. So minus 825. Now moving from point A till point B, there is no other shear force, so it will remain same till this point. Clear? So I will point out this point. So this shear force will remain same till this point. Okay, now here at point B we have RB which is acting upward. So RB is 1725. So minus 825 plus 1725 will bring it to 900. So I will write it here. This point is 825 and 900 is this point. There, so shear force will change from minus 825 to 900. Okay. Now moving from point B till end, there is no other shear force you can see, so it will remain horizontal. Clear? And at end you can see you have 900 downward, so it will cause it to move downward. So this will be your shear force diagram. Now we'll draw the bending moment diagram. So for bending moment diagram, I will draw a horizontal line, and this x will be in meter. So here we have moment that will be in Newton into meter. So let one division is equal to 200. I will choose another color. So my downward is minus 200, minus 400, minus 600, minus 800. Clear? At point A, you can see this at this point till this point. If we divide it into two portions, because here you can see there is external movement till this point. So this area will be equal to area under the shear force diagram will give you bending moment, and this area is 825 into this length is 0.8. So 825 multiply by this minus will give you minus 660. So at this point the bending moment will be minus 660. So we look at minus 660. Let 660 minus 660 is this point. There. And you can see that shear force is a horizontal line with 0 degree. So bending moment will be 1 degree higher, and slope will be decreasing, and it will be a straight line. Okay. At this point we have moment is equal to 0 because x is equal to 0. Now you can see you have a clockwise movement which is 600. So while drawing it on bending moment diagram, it will be taken as positive due to convention. So minus 600 plus 660 plus 600 will be minus 60. So shear force will change to minus 60. So let minus 60 is somewhere here. This is minus 60. So shear force will change from minus 660 to minus 60. Now you can see you have remaining this portion which is equal to minus 8. This area will be equal to 825 into 0.8, which is equal to minus 660. So minus 60 minus 660 will give you minus 722. So at this point, the bending moment will change to minus 720. So 720, let's say 720 is somewhere here, here. This is minus 720. And shear force is a horizontal line with area negative. So bending moment will be 1 degree higher and slope will be decreasing. It will be a straight line like this. Okay. Now we have only left with the final area, which is this one. So this area is 900 multiplied by 0.8. Then that will be equal to, this area is positive, this is 720. So minus 720 plus 720 will bring it to 0. So moment at this point will be 0. And you can see that shear force is a horizontal line with 0 degree. Bending moment will be 1 degree higher, and this area was positive. So its slope will be increasing. So I will join these 2 points like using a straight line. And that is BMD, bending moment diagram, for this shaft. Clear? And that was all about this problem 6-36. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it, and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. Problem 6-64. This problem is taken from chapter number 6, that is bending, and book name is Mechanics of Material by R.C. Hibbeler. Statement is the axle of freight car is subjected to wheel loading of 20 kips. If it is supported by two channel bearing at C and D, determine the maximum bending stress developed at the center of axle, where diameter is 5.5 inch. So you can see this is the axle of freight car, and these wheels are subjected to 20 kilonewton loads. There is a general bearing at C and D. Clear? So you have to determine the maximum bending stress at the center of the axle. Diameter is 5.5 inch. So let's start with the solution. So if you remove this general bearing at C, clear, so there will be a reaction force that will be taken as downward because these two forces are upward. So that is represented as RC. And if you remove this bearing at point D, so you will be having a reaction force which will be presented as RD. So we will find this RC and RD by using equation of equilibrium. So first equation of equilibrium is that sum of all moment about point C is equal to 0, and taking the counterclockwise moment as positive. So about point C, first movement will be this 20 kips into perpendicular distance is this 10, and this is producing counterclockwise, it will be positive. The second movement about point C will be this 20 kips, and perpendicular distance is now 70, and it is also producing counterclockwise, so it will be positive. The third movement will be due to this RD, and now perpendicular distance is 80, and this is counterclockwise, so it will be negative. And the sum of all movement about point C must be equal to 0. So I will write 20 into perpendicular distance is 10 plus 20 into perpendicular distance is 70 minus RD into 80 is equal to 0. So we will get 200 plus 1400 is equal to 80 RD. Clear? And RD will be equal to 1600 divided by 80, and that will give you 20 kip. Now this is RD, and we can find RC by using equation of equilibrium, that sum of all forces along y direction must be equal to 0, and upward force is taken as positive. So you can see RC is downward, 20 kips is upward, this is upward, and this is downward. So I can write minus RC, clear, plus 20 minus plus 20, and RD is minus 20 is equal to 0. So from here RC will be also equal to 20 kips. You have RC and RD, so we can easily move toward shear force and bending moment diagram, from where we can get the maximum bending moment at the center. So I will draw the vertical line from the end of this beam. We'll solve this question by using two methods. First is this one, clear, from the end of this beam, and there is a horizontal lines which show the length in x in inch. On y-axis we have vertical shear force that will be in kips. Let each division is of 10 kips, so 10, 20. Similarly, minus 10, minus 20 you can take as per your own scale. Now you can see uh, at point C there is a RC which is downward, and RC is to 20, so it will be minus 20. So your first point will be this one. Clear? At point A, clear, you can see moving from RC till A there is no other shear force, so it will remain horizontal till this point. So let me draw it like this. It will be horizontal. Now at point A we have plus 20. So minus 20 plus 20 will be equal to 0 at this point, and shear force will change from minus 20 to 0. Okay. Now moving from point A till point B, there is no other shear force, so it will remain horizontal till this. Clear? And we will get a straight line that will be 0. Clear? And at point B we have plus 20. So 0 plus 20 will bring it to plus 20. So it will move toward vertically upward, and this will be plus 20. Now moving from point B to D, there is no other shear force, it will be remain horizontal, and at end we have RD which is minus 20 will bring it to 0. So it will be like this. So this will be your shear force diagram. Now by using this shear force diagram, we'll draw the bending moment diagram, and again you can see you have a horizontal line that will show you length in inch, and we will have movement on y-axis that will be kips into inch. Let each division is 100, so minus 100, below is low is minus 100, so minus 200. Now first area under the shear force diagram is this area, and you can see this is rectangular, so height is minus 20 and width is 10 inch. So minus 20 into 10 will be equal to minus 200. So at this point we have minus 200. So let me plot this point. This will be minus 200. Now you can see shear force is a horizontal line with 0 degree, and this area is negative. So bending moment will be 1 degree higher. It will be a first degree line, and slope will be decreasing. So we'll get this line. Okay. Now you can see that this shear force here is 0. So bending moment will be remain constant till this point. Clear? So I will make it flat line because it will be constant. Now here we have another area which is positive, and this is equal to 20 into 10, and that is 200. Clear? So here this is minus 200 plus 200 will bring it to 0 at this point. Clear? So this will be your point. And you can see that shear force is a horizontal line with 1 degree, and this slope, this is positive area, so bending moment will be 1 degree higher and slope will be increasing. It will be a straight line, first degree straight line. So this is your bending moment diagram. Now from bending moment diagram, bending moment diagram, you can see that if this is the mid of this beam, clear, or center of this beam, so at center we have maximum bending moment is 200. The absolute value is 200 moment. So we will get maximum bending moment is equal to 200 kip into inch, and we have been asked to find out the maximum bending stress developed at the center of axle. So we know that maximum bending stress is equal to maximum bending moment into C divided by I. C, because this shaft is circular and the diameter is given, so we'll find the C is radius. So diameter is 5.5 inch, so radius C will be equal to D divided by 2 and 5.5 divided by 2 inch. C will be this one. So that will give you 2.75 inch. Clear? So bending's maximum bending stress is equal to maximum bending moment. So maximum bending moment is 200. C is the distance from center till outermost, which is the radius. Clear? This is C. So it is 2.75 divided by moment of inertia I, and I for circular I is equal to pi by 4 C power 4 for circular shaft. So you can calculate it pi by 4 into 2.75 power 4. So you can put it over here pi by 4 into 2.75 power 4. So when you calculate it, you will get maximum bending stress comes out to be 12.2 KSI, which is the answer of this question. Clear? Now we'll solve it by using another method. This was using shear force and bending moment diagram. Now we'll solve it by using another method. For that, I will cut this shaft at the center and draw the free body diagram. So it will look like this, that let this will be the shaft. Clear? At this end, you have a loading of 20 kips. Clear? And at this point, we have a wheel at 10 inch and over which 20 kips is upward. 20 kips is upward. This distance is 10 inch. Clear? And the remaining distance is, let me check it, the half of this will be 30. Clear? So the remaining is 30 inch. So when you cut it, so you will be having shear force as well as moment. Clear? So we are interested to find out the maximum moment at the center. So for that, I will apply the equation of equilibrium, that sum of all moment about point 1 is equal to 0, and taking the counterclockwise moment as positive. So about this point, we have first moment is 20 into perpendicular distance is 40, and this is producing counterclockwise movement, so it will be positive. The second movement will be 20 into perpendicular distance is 30, and this is clockwise, so it will be negative. And third movement, which is reaction movement, that is clockwise, it will be also negative, and their sum must be equal to 0. So I will write 20 into 10 minus 20 into 30 minus m is equal to 0. So m will be equal to 200 minus 600. Clear? And this will be 20 into, this is not 10, this is not, this is 40, because you can see 20 into perpendicular distance is 40. Clear? So this will give you 800, not 200. So movement will be equal to 200 kip into inch, which is, you can see this is exactly the same which we have taken over here at the mid, at this mid. Clear? At somewhere here. Okay, now you have this moment, so you have this formula, maximum bending moment is equal to maximum bending stress is equal to maximum bending moment into C divided by I. So 200 C is 2.75 divided by I, which we have calculated like this. So pi by 4 into 2.75 power 4. And from here you will get maximum bending stress is equal to 12.2 KSI. So this is the way where we can solve this problem by using two methods. And that was all about this problem 6-6. 64. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. In this video, we are going to solve problem 6-67 and 6-68, and this is from chapter number 6, Bending, and book name is Mechanics of Material by R.C. Hibbeler. So let's start with the 6-67. The statement is the shaft is supported by smooth journal bearing at A and B that only exert vertical reaction on the shaft. If D is equal to 90 millimeter, determine the absolute maximum bending stress in the beam. Sketch this stress distribution acting over the cross section. So you can see this is beam that is made up of shaft, and there are two general bearing at A and B that exert vertical reaction. The load is shown from A to B. There is a uniformly distributed load of 12 kilonewton per meter, and from B till end there is a uniformly decreasing load or triangular load. So diameter is also given, that is 90 millimeter. So you have to find the absolute maximum bending stress, and then you have to show the stress distribution over this cross section. So let's start with the solution. So first step is that if you remove this general bearing at point A, so there will be a reaction force exerted by general bearing on this shaft, which is Ra, and similarly if you remove this general bearing at B, so there will be reaction force Rb. So first we will find this Ra and Rb by using equation of equilibrium. Now you can see from A to B there is a uniformly distributed load of 12 kilonewton per meter. So when converted it into a point load, it will be equal to 12 over the length over which it acts, that is 3, and that is 36 kilonewton, and that will act at the half of at the mid, which means that this will be 3 meter, 1.3 divided by 2, which is 1.5 meter, and this remaining will be also 1.5 meter. Similarly, you can see you have a triangular load, so when you convert it into a point load, so it will be equal to 1 over 2 into this 12, and the length is 1.5. So that will give you 9 kilonewton, and that will act at a length of L by 3. So L is here 1.5. Here this is 1.5 divided by 3, which is equal to 0.5 meter, and this remaining will be 1 meter. Okay, now we'll apply equation of equilibrium. So first equation of equilibrium is that sum of all the moments about point A is equal to 0, and taking the counterclockwise moment as positive. So about this point A, the first moment will be this load, which is 36, and perpendicular distance is 1.5, and this is clockwise, so it will be negative. So I will write it first. This 36 into perpendicular distance is 1.5, and this will be minus. The second moment will be due to this RB, and perpendicular distance is 3, and this is counterclockwise movement, so it will be positive. So I will write plus RB into 3. The third moment will be produced due to this load, which is 9 kilonewton, and now perpendicular distance is 1.3 plus 1.3 plus 0.5, which is 3.5, and that is clockwise, so it will be negative. So I will write minus 9 into 3.5 is equal to 0. So again, when you calculate this, and you will get RB is equal to 28.5 kilonewton. This is the value of RB. Clear? Now we'll find RA by using equation of equilibrium, that sum of all forces along y direction must be equal to 0, and upward force is taken as positive. So RA is upward, so RA, this 36 is downward, minus 36, this 9 is also downward, minus 9, plus this RB, which is 28.5, is equal to 0. So from here RA will be equal to RA will be equal to 16.5 kilonewton. Now you have both RA and RB, so we will move to draw the shear force and bending moment diagram. For that, I have to draw the vertical line from the end of the beam. Clear? And we will draw the shear force and bending moment diagram. Okay. So here we will take a horizontal line to show length x in meter. On y-axis we have shear force that will be in kilo Newton. Let each division is 5. So 5, 10, minus 15, plus 15, plus 20. Similarly, minus 5, minus 10, minus 15, and minus 20. Okay. So at point A, you can see you have RA, which is 16.5. So first point will be 16.5. Let this is 16.5 kilo Newton. Now at point B, this is the point, this is length of 3 meter. Clear? 3 meter. Now at 3 meter, we have, at this point, we have, at there is a uniformly distributed load over a length of 3 meter, so it is 36. So at this point, load will be equal to 16.5 minus 36, and that will be equal to minus 19.5. So we will locate minus 19.5. So 19.5 will be somewhere here. This will be 19 point minus 19.5. Now you can see that this load is a horizontal load with a 0 degree, so shear force will be 1 degree higher, and this load is downward, so slope will be decreasing. It will be a first degree line and slope will be decreasing. It will be straight line joining these 2 points. Let me join it again. Let me join it by using ruler. Okay, so I will join them by using this ruler. Okay, I don't know why I am facing difficulty today. Okay, let me try like this. It will be a straight line joining these 2 points. Okay, now you can see that I have joined these 2 points. Clear? And at this point we have RB upward, which is equal to 28.5. So minus 19.5 plus 28.5 will give you 9, plus 9. So at this point shear force will change to plus 9. Let this is plus 9. So shear force will change to plus 9. And here you can see you have a uniformly decreasing load, so this will be equal to, that is, you can see that is 9, and that will be downward, so it will be minus 9. So plus 9 minus 9 will bring it to 0 at this point. And you can see that this load is a 1 degree line and slope is decreasing, so bending, so its shear force will be a 2nd degree curve, and it will be like this. Clear? It will be like curve, not a straight line, but it will be like a curve. So this will be your shear force diagram. Now at this point you can see we shear force is 0, and at this point the bending moment will be maximum. So for that we will find this x. So for x we will cut this beam at any length x, and we'll draw the free body diagram of this beam. So this is RA, which is 16.5. This is the length X over which we cut this beam, and there is a uniformly distributed load which is equal to 12 kilonewton per meter. There will be a shear force, clear, and this shear force will be there, and there will be a bending moment. So we will find the equation of shear force. Now you can see this, when this uniformly distributed load is converted into point load, so it will be equal to 12 into the length over which it acts, and that is X, and that will act at a distance of X by 2 at half of this length. So this will be X by 2 and this will be X by 2. Now we'll find this shear force equation by using sum of all forces along y direction must be equal to 0 and upward force is taken as positive. So you can see 16.5, which is acting upward, minus this 12x, that load is downward, and this minus v is equal to 0. So from here this v will be equal to 16.5 minus 12x. If you put x is equal to 0, so you can see that shear force at x will be equal to only 16.5. Okay, now we are going to find the value of x for which shear force is equal to 0. So put v is equal to 0. So 0 is equal to 16.5 minus 12x, and 12x is equal to 16.5. So x will be equal to 1.375 meter. Clear? So this is the length at which x is equal to 1.375 meter, at which we have shear force is equal to 0. Now we will draw the bending moment diagram. So for that I have to draw vertical line from the end of this beam, a horizontal line that will show x in meter, and on y-axis we have moment that will be kilonewton into meter. Let each division is 5, so 5, 10, 15, similarly minus 5, minus 10. Okay, the first area under the shear force diagram is this one, and this area, let this is A1, and this area A1 is equal to area of this, as this is triangle, so its area is equal to half into height into its width. So 16.5 and width is 1.375. So 16.5 multiplied by 1.375, and that will be equal to 11.34. So at this length we have 11.34. So let 11.34 is this point, 11.34 kilonewton into meter. Now you can see that shear force is a 1 degree line and its area is positive, and but slope is decreasing. So bending moment will be second degree curve and it will be clockwise. So we can join these 2 points by using, it will be a second degree curve there like this. Now the second area is this one, and this area A2 is equal, this is also triangular, so its area is equal to half of this width, which is equal to 3 minus 1.75. Clear? And height is this 11 19 point minus 19.5. So when you calculate it, you will get this area is minus 15.84. So 11.34 minus 15.84 will is equal to minus 4 at this point. So at this point the moment will be minus 4.50. 4.50 minus, and again this will be, you can see that shear force is a horizontal line with 1 degree. So bending moment will be second degree curve and slope is decreasing, so it will be again clockwise. So we will join these 2 points again like a curve. So it will be like this. Now the third area is this one, and you can see this area is E3, and this area will be equal to BH over 3, because this is parabolic spandrel and its area is equal to BH by 3. So B is this one, which is 1.5, and H is 9. And when you calculate it, you will get this area will be equal to plus 4.50. So minus 4.50 plus 4.50 will bring it to 0. And you can see this is a second degree curve. So bending moment will be third degree, and it will be like this. It will be like this. Clear? So this is your bending moment diagram. Now from BMD, bending moment diagram, we can see that maximum bending moment is equal to 11.34 kilonewton into meter. So we know that maximum bending stress is equal to maximum bending moment into C divided by I. Diameter is given as 90 millimeter. So diameter is 90 millimeter. So radius C is equal to D divided by 2. So 90 divided by 2 is equal to 45 millimeter, and in meter it is equal to 0.045 meter. And what about JI? Second moment of inertia of this circular shaft, it is equal to pi by 4 C power 4, and that is pi by 4 into 0.045 power 4. The unit will be meter power 4. So put this in this formula. Maximum bending moment, bending stress is equal to maximum bending moment, which is 11.34, and we will convert this kilonewton into 10 raised to power 3. Multiply by C is 0.045, divide by I, which is pi by 4 into 0.045 power 4. So when you calculate it, you will get maximum bending moment is 158 into 10 raised to power 6 Pascal, Newton per square meter, that is Pascal. So 158 megapascal. This is maximum bending stress, which is the answer of the first part of this question, which is question 6-67. Now we'll move to solve problem 6-68. And what's the statement? The statement is the shaft is supported by smooth journal bearing at A and B that will exert vertical reaction on the shaft. Determine smallest diameter D if allowable bending stress is 180 megapascal. So we have been given allowable bending stress, that is 180 megapascal. Okay. Now we know that maximum or allowable bending stress is equal to maximum bending moment into C divided by I. So we have to find the diameter for this allowable bending stress. C is not known. We have to find this. So we know that allowable bending stress is 180 megapascal. So 180 into 10 raised to power 6. Maximum bending moment, from this diagram you can see 11.34 kilonewton into meter. So 11.34 into 10 raised to power 3. C is equal to diameter divided by 2, and I is equal to pi by 4 C power 4, and C is D by 2 power 4. So from here you will get this will cut with one of this, so we will left with 180 into 10 raised to power 6 is equal to 11.34 into 10 raised to power 3 divided by pi by 4 d by 2 power 3. Clear? Now d by 2 power 3 will be equal to 11.34 into 10 raised to power 3 divided by pi by 4 into 180 multiplied by 10 raised to power 6. And when you solve this d cube will be equal to 8 multiplied by 11.34 into 10 raised to power 3 divided by pi by 4 into 180 into 10 raised to power 6. And this d power 3 will be equal to 0.0006416 and d cubic cube cubic square root will be equal to cubic square root 0.0006416 and from here you will get this d will be equal to 0.0862 meter, or this d will be equal to 86.3 millimeter, which is the answer of our second part. Remember, if you have been given problem 6-68, so you will need maximum bending moment for which you have to perform all these things. Clear? Once you get maximum bending moment, so you can just put in this formula. Now, the last thing is that in part first, we have been asked to find the shear stress distribution over the cross section. So let me draw the cross section. If this is the cross section that is shown over here, for example, if this is the rod, clear, like this, and this is the center or neutral axis. So at this point we have maximum bending moment, which is this one, clear, and it will be like this, it will be like this. And similarly the same is the case for this one. You have maximum bending moment and it will be like this. Clear? So you can see on the top we have compression. Clear? You have to like this, and on bottom you have extension, tension. So this will be your stress distribution over the cross section. And that was all about this problem 6-67 and 6-68. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching.